on. I am not going to embarrass you by asking you straight up front how many of you solved the problem that I left you with last time, but we're going to have a look at it. And I will take any volunteer who can just tell me what the answer is. Don't need to tell me how you got it. Just tell me the answer.
0.
Yes, it's 0. So I'm about to show you one of the ways in which you could do that. This may not have been the way that you did it. Here goes. Right. It's called the sandwich theorem. What do I know about sine function? Well, I know that it varies a lot, but isn't the biggest number it ever gets to is 1, and the smallest number, the sine of anything, is -1, right? It never gets bigger or less than those two numbers. So when you square it, won't the smallest value be 0? Right, because -1 squared becomes +1. So I know on this side, it's that. And on this side, the biggest it can be is 1. So I know that this always takes values between this number and that number. Well, that's 0. Isn't 2 over 2 to the power of n, if you make n go infinite, isn't that 2 to the power of infinity? Isn't that also 0? And the guy in the middle, the one I'm trying to get the answer to, he is sandwiched between a 0 and a 0, which makes him 0. So there's my proof. It's called the sandwich theorem. Now, that is not the only proof or technique that you could have used. So some of you may have found other ways to do that. As far as WebAssign is concerned, you just type in 0 and it's finished. Because WebAssign only essentially is for a placeholder for the answer. It doesn't expect to see the working. We expect to see the working, but WebAssign only expects to see what the final answer looks like. So there are lots and lots of different situations. I'm going to try and cover a few more today and then move on to series. So how about this one? This is the list of power functions. And what I mean by that, I'm not talking just about x cubed as a power. I'm talking about how powerful a function is. In other words, how big does it get for small values of n? Right, at the top end, n to the power of n is the most powerful function in the universe. Give you an example. Do you know when n is 10, which isn't a big number? That guy is 10 to the power of 10. Right, 10 to the power of 10, 100,000 million. Huge. Next door to that, powerful but not quite as powerful, is n factorial. You know, like 10 factorial is huge, but not as big as 10 to the power of 10 is. Next fella. Two to the power of n. For instance, if n is 10, 2 to the power of 10 is 1,024. It's nothing like 100,000 million, right? Or 10 factorial, which I'm guesstimating is about 1 million. That's about 1,000. Next, after that type of guy, right? You get n squared. After n squared, you get square roots and cube roots. And right at the tail end, you get natural logs. Now, if you can memorize this list of power functions, it will allow you to find the limits, the answer to limit questions that involves any two of these being divided. So let's give you an example. The limit as n tends to infinity of 2 to the power of n over n squared. Now, in these questions, both of the terms come from here. And if they do, there's only going to be two possible answers. The limit is going to be 0 or it's going to be infinite. Right? There isn't anything in between. The only time you get in between is when a 2 to the n and a 3 to the n, right? When they work together, you might get something, but that's not likely. Right? So 0 or infinity is where we're going here. Which one of those two guys is the most powerful?
2 to the n.
And that makes it the biggest guy on the top and the small guy on the bottom. That gets you infinity. So we are not doing algebra, we're just doing memory. Now, if you do it this way around, isn't the big guy on the bottom? You don't really care about the top guy. If the big guy's in the bottom, you get essentially 1 over infinity, you'll get 0. So look at your fraction. If the biggest powerful function is on the top, the answer is infinity. If the biggest power is on the bottom, the answer will be 0. And that's all you need to know. And when the answer is infinity, the way that WebAssign does it is, I think you type in DNE. That's their placeholder for this. So let's try one. What would be the limit as n tends to infinity of log n over n cubed? 0 or infinity?
0.
0.
Agree, n cubed? N cubed is one of these guys. Although I'm calling this n squared, do you know that's a placeholder for n squared, n cubed, n to the 4, n to the 5, n to the 55, right? Things like that, right? And so the big guy's in the bottom, and that makes the answer 0. What about the limit as n tends to infinity of n factorial over n to the power of 100? Which one of them is the most powerful, top or bottom?
The top.
And that makes the answer infinity, or as WebAssign would say, does not exist. Are you comfortable with this is the list of power functions, right? How powerful they are. And if you've got a fraction, you just choose, you just look at which one's the most powerful, which is the big guy. If the big guy's in the top, it's infinite. And if the big guy's in the bottom, it's 0. End of story. So
is the 2n similar to the n squared, or the 2 to the power of n, to where it could be 3 to the power of n or 4 to the power of n?
yeah, so that's
Okay.
just a placeholder for all the big numbers to the power of n, right? 5 to the power of n. These two are pretty much it. Now, you might stick numbers on it. And here's a cool thing. You might stick a 3 there and a 5 there. Which means absolutely no difference to the answer. Ignore them. The answer will still be 0 or infinity. Five n squared is still never going to beat a 2 to the n, or 10 times 2 to the n, or any other version of 2 to the n, right? 2 to the n eventually gets so big it will swamp the other expression in value. Are we good?
So that would still occur if you had like a combination, like let's say you had 2 to the n plus n factorial over like n squared.
Yeah. In this case, n factorial and n cubed, and the big guy's on the top, so it's infinite. right? So that's quite helpful, isn't it, for easy checking? You really just need to say, okay, where's the big guy, right? Where is the most powerful function? And wherever it is, that's going to be the direction of the entire limit. If it's on the top, infinite. If it's on the bottom, 0. Any more questions, or should we move on? We're good? Right. Okay. Look at these two guys. This one's similar to 17, this one's similar to 19. I'm not doing the whole question, I just want to show you that you need different approaches to different situations. Both questions want to know what's the limit as n tends to infinity, right? The answer could be infinite, could be a number, could be 0, right? 0 is just a number, of course. But the technique here is maybe not obvious. It's going to be L'Hopital. And you might say, but it isn't a fraction. I agree, it's not a fraction, but I can make it one. Isn't n over 2 the same thing as 2 over n on the bottom? Now you do L'Hopital on that and you will get an answer. How about this second one then? It is not directly L'Hopital. It's not a L'Hopital question. Not directly, at least. What do you think you might have to do in this particular situation to help you find the limit?
Make one log.
I agree. And isn't the rule for 2 logs subtracted the first log divided by the second? Agreed? Now, what you can do with limits is that you can change the order in which you calculate the limit. In other words, can't I find this limit and then say the log of that answer is what I need? That's allowed. So logs and limits, logs and sines and square roots and so on can do it. Now that guy there, you can do a number of ways, but it's pretty easy to do. If the answer was 5, the final answer wouldn't be 5, it would be the natural log of 5, right? Because that natural log is there. Right? Now in that same vein, do you know if you wanted to know what the limit of this fella was? What you could do is switch the limit in the square root. So find that, and then the square root of that is what you're looking for. Right? So that's essentially you simplify the question by only finding the limit of a fraction, which is pretty easy to get. And if the answer is 0, that's fine. If it's 22, it's fine. If it's infinity, it's fine. Whatever that answer is, take the square root of it, and that's the answer to the original problem. Or take the log of it. Or can you imagine a big ugly thing, brackets around it to power 100? Well, couldn't you just find the limit of what was inside the brackets? Once you got that answer, raise that answer to the power of 100, and you'd be fine. So there are a lot of different algebraic tricks to finding limits, right? It's not just one size fits all, right? You've got to look at the information that's in front of you and figure out what to do. So we're now at the end stage. How do you find formula for sequences? And here we go. Here is my first question, my first sequence. 1, 2, 4, 8, 16. And I need a formula. that allows me to find the first, second, third, fourth, fifth, and so on terms. So I want you to think of n is equal to 1, when it's 2, when it's 3, when it's 4, when it's 5, and then can you imagine an n, and that's what is going to go there. Any suggestions? What would you do with 3 to get 4 as an answer? What would you do to 4 to get 8 as an answer?
I think you could do 2 times a to the n to the negative -1.
That is a very interesting answer. That will actually do the job. So you don't need the extra 2, but you were pretty much nailed it. Now you might think, whoa, that was out of the blue. So let me tell you that there are some strategies. When you have a sequence, do you notice that you're multiplying everybody by 2 to get the next number, right? So you can imagine a sequence where you start off with a number and then you go times 3, times 3, times 3, times 3 kind of thing, right? When you do that, your answer is going to be whatever that is to the power of n, maybe n minus 1, maybe n plus 1, but it's always going to have that basic look to it. And then you can just tweak it. So let me do a tweak. When n is 1, the answer is 1. Well, if it had been 2 to the n, would it not get me the wrong answer? Right? But if you used that, don't you get 2 to the 0, which is 1? How about this fella then? I'm going to start with 1, negative a sixth, plus 136, negative 216. And this one is similar to question 28. Okay. What number do you multiply to get from here to here, and then here to here, and then here to here?
-1/6.
Agreed. And the answer is that guy, and sometimes that guy. You have to play about with the powers. Which one of those 3 do you think actually gets you that fella? If you plug in 1, which one of these 3 would give you the answer 1?
N minus 1.
Yep. So that's the one that you would use. Try this fella. They like ones. 1, 3, 5, 7, 9. You're not multiplying this time. Do you notice that to get from one number to the next, aren't you adding 2 each time? By the way, these sequences are called geometric sequences. Anything where you start with a number and multiply all the time is geometric. These are called arithmetic, if you wanted to know them. When you have an add 2 all the time, your formula will always be add 2 gets you 2n. Add 7 all the time will get you 7n. You then have to do plus or minus a number. Now, 1 gets you 1, 2 gets you 3, 3 gets you 5. So all I need to do is I need to figure out what number do I need to add or subtract so that when you plug in 1, the answer is 1. Well, let's see, if you plug in 1 here, you get 2 lots of 1 plus or minus a number, and it has to equal 1. Okay, isn't that 2 plus or minus a number? What do you need to fix this?
A -1.
Now, once you've figured out that you needed to subtract 1, that will work for all of them. Let's prove it to you. That's the 5th number, right? Shouldn't the answer be 9 then? 2 lots of 5 take away 1? Yep, it's 9. So if you have a sequence where you start with whatever that number might be, and you add 2 and you add 2 and you keep adding 2, you know it's going to be 2n, and then it's just a matter of tweaking it. Is it 2n plus 5? Is it 2n take away 1? You know, whatever it is. So this is an example now, our last one, 29. Are we multiplying all the time here or adding all the time?
Adding
And what are we adding?
+3.
So won't that get me 3n? Okay. To make it work then, don't n equals 1. Shouldn't that get me the answer 5?
Mhm.
How do I amend this formula to make that happen? 3n
3n plus 2.
Add
and you're done. Do you see how that works? If you have a sequence where you add 7 all the time, it's going to be 7n plus a number, take away a number. It's just a matter of tweaking it, right? What number makes the whole thing work? And you only need to make the first one work, and everything else will come. I mean, I could check it just to make sure. Shouldn't the 4th number be 14 then, right? 3 lots of 4 add 2, bingo, 14, it works. Easy to check. There are only 3 questions at the end. I think we've covered the options here, so hopefully you'll be able to write down a formula for them. Are we good to go? Any questions before I move on? No, I'm cool with that then. Let's get started on our second section then. In fact, the rest of chapter 11 is going to deal with things called series. So what is a series? A series is the sum of a sequence. So if you take a sequence and you add up every single number in that sequence together, we call that thing a series. Let's give you an example of some series. That is an example of a series. It's a very interesting one. It's called the harmonic series. Anytime a series gets a name, you know it's probably going to be useful. You're going to do it a lot. And the harmonic series crops up quite a few times in this particular chapter 11. Now, what are you typically going to do in a situation like that? Well, I'm going to call it S. And we are going to find what that is equal to. Now, you might say, well, you're adding up an infinite number of things. Surely the answer is always going to be infinity. Well, in many cases, including this one, that's exactly true. It is infinite. It's infinitely large, right? Even although you're adding smaller and smaller terms, you're still adding up an infinite number of them, and so the final total is infinitely large, right? But here's a different one. This is called a geometric series. Do you know this one is equal to 2? Now, when you look at them, they are very similar. Doesn't this just one get smaller quicker? In other words, by the time you get to the 5th term, you're here, a 16th, whereas here you're only at a 5th. That subtle difference is enough to make this series add up to a limit of 2, and this series to basically being infinitely large. So we are going to be spending most of our time finding out, what does a series sum to? Does it sum to a number like 2, or does it sum to infinity? And we use jargon expressions. When the answer is infinite or undefined in some way, we will say that the series diverges. You don't even mention the word the number infinity. You just say it diverges. And when it is equal to a number, in this case 2, you will say that it converges to 2. I'm going to do a little side issue here. This particular series was known thousands of years ago by the Greeks, and it freaked them out. And they had a story attached to it. So here is the story. That's a frog. Okay. There, it's a frog. This frog in this story was 2 meters, or whatever the units the Greeks had at the day, 2 units of distance away from a well. And this frog in this story, on its first jump, jumped a meter. But every jump after that, it was a little bit tireder, so it only jumped half as much. So its second jump, it did a half. And then its next jump, it was a quarter. And then its next jump, it was an eighth. And that little frog kept on jumping. And the problems that the Greeks had is that they didn't have a very good concept of infinity. In fact, I'm not even sure they had the concept of infinity. So the Greeks said, does the frog reach the well?
No.
It keeps jumping. And no matter how much it jumps, isn't there still a little bit left? And its next jump is only half that distance, right? So it never reaches the well. But then the frog is jumping forever. And it's still moving forward forever. So why isn't it reaching the well? Can you see that their brain was a little bit confused? That it has some kind of, it should reach it. I mean, if you keep doing it and you're getting closer and closer, eventually you're going to get there, right? In a kind of pseudo kind of logical way. And that really freaked them out. The Greeks did not like infinite sequences. They came up with contradictions. They came up with some other weird contradictions based on similar ideas. You can look at this one up if you're interested. They did a thought experiment on an arrow being shot into the air. And the logic that they used proved that the arrow couldn't travel. It had to be stationary. Which we know is wrong, and they knew it was wrong. But it was because they were using poor definition of infinitely small. So let's return back to our worlds. I'm telling you that converges to 2. Let's talk about a convenient way of writing down series instead of writing them like this. Oops, let's do it again. Hopefully, have you seen sigma notation somewhere? Right. Now, in sigma notation, 1 plus a half plus a third plus a quarter can be written down like this. Basically, sigma says the sum of using k equals 1 to infinity of that guy, or n equals 1, or p equals 1, or any other letter of the alphabet. They are mathematically equivalent. That k equals 1 gets you this guy. Then you put k equals 2, then you put k equals 3, and you do it for eternity. Let's do this fella. Isn't the sequence 1, comma, a half, comma, a quarter, comma, an eighth, comma, 16? Remember that sequence? 1, comma, a half, comma. Didn't we do that about 10, 15 minutes ago? Can you remember what its formula was?
One half to the n to the negative.
N to the negative 1. Oops, well, k in this case, n in that case. I'm not going to start doing 2 letters, and the reason I'm not doing that is that sometimes this textbook changes the sigma for no good reason that I can think of. It's going to be I equals 1 to infinity, k equals 1 to infinity, or n equals 1 to infinity. So we just get used to any letter of the alphabet can be used here as long as you're consistent. Right. So that's what this guy looks like. So here is our first test, geometric series test. What this test does is it will tell you if a particular geometric series, that's one where the sequence was a number and then you times 2 times 2 times 2, or times a half times a half times a half, right? Something like that. Geometric series test. And it says for any GS, geometric series, sigma n equals 1 to infinity, a r to the n minus 1. So that is essentially the generic version of every geometric series in the universe. So for any geometric series, it will converge provided the absolute value of r is less than 1, and it will diverge if the absolute value is greater than 1. So a geometric series test says if you've got a geometric series and this guy is less than 1, it will converge, and if this guy is greater than 1, it will diverge. And if it converges, the sum of that series will actually be whatever a over 1 minus r is. So it's just a bit of memory work. You're going to look at geometric series, and if you can find this fella R, which is called the common ratio, if its absolute value is less than 1, it's going to converge, and if it's greater than or equal to 1, it's going to diverge. Okay, let's do one. I'll start with 3, right? And then I'll multiply by a half, then multiply that by a half, then multiply that by a half, forever, right? I know that's a geometric series. From one number to the next, aren't you multiplying by, in this case, a half? Agreed? Now, the first term is A, in this case 3. The common ratio is a half. So I know that this series converges. Because the absolute value of R, which is a half, is less than 1. And I know that this series adds up to A over 1 take away R. And A is 3, and 3 take away half ends up being 6. Here's another geometric series. Oh, by the way, they will tell you it's a geometric series, although you should be able to tell by looking. Let's do the frog one. Didn't I say that this fella was going to add up to 2, converges to 2? A is the first number. The common ratio is a half again. This series converges because that guy is less than 1. And what does it add up to? The series adds up to A over 1 minus R, 1 over 1 take away a half, 1 over a half, it adds up to 2. So it's a very simple test. If they are asking you, does this series converge or diverges, you find the common ratio. If the common ratio is less than or less than 1, it converges. And if the common ratio is greater than 1, it diverges. And if it does converge, you can even use this formula to get the answer. Are we okay so far with this test on a series? Do one more and then I'll prove it to you. There's a geometric series. The first number is 3. What's the common ratio?
Times 4.
4. Would you agree that the absolute value of 4 is definitely bigger than or equal to 1? So it diverges. Okay.
So a shortcut is if we see a fraction, do we instantly say it converges?
If you see a fraction less than 1, yes. But be careful, because sometimes the fraction might be 3 halves.
Okay.
Right. But if it's a fraction less than 1, positive or negative doesn't matter, right? If it's a fraction less than 1, it converges. Right. Now, I said I'd prove it to you, so I don't like magic, so I'm going to do that. Suppose you start off with a number A. If you multiply it by R, don't you get AR? If you multiply that by R, don't you get AR squared? And if you multiply that, you get AR cubed. Isn't that basically what every geometric series in the world looks like, right? You start with a number and then you keep multiplying by R. So I'm going to call that S. So far, so good. Now, I'm going to find R times S. So you imagine taking this and multiplying all of the terms by R. So this guy gets you AR, and this guy, when you multiply it, gets you AR squared, and this guy, when you multiply it, gets you AR cubed, forever. Do you notice that they're almost the same? There's just one term difference. So far, so good. Now, what would happen if you took the top and subtracted the bottom? So you take the top line and subtract the second line. Well, if you take all of this and subtract all of that from it, isn't the only thing left alive A? Now, you notice that S's are common to both these. And what do I do to find S then? What do I do to both sides to get S?
Divide out the 1 minus R.
And can you see that's the formula for what a geometric series adds up to? And that's the proof of it. Now, I wish I could prove a lot of the things that are going to happen in this class, but to be honest, I won't be able to. The math that you need to prove them is quite advanced. You're just going to have to trust me when I tell you things in the future, right? But at least for this one, can I kind of pseudo-proof it to you so it's not totally magic? So far, so good? So if I give you a geometric series, are you comfortable you can tell if it converges or diverges? And for the ones that do converge, are you comfortable about how you would find out what its sum is? So I'm going to give you one to try right now. No pressure, you got 1 minute, go for it. Coming up on it. There it goes. The first term is 2. Be a little bit careful here. What is the common ratio?
Negative
Negative
1/3.
1/3.
Agreed. Now, isn't the absolute value of negative 1/3 less than 1, so it converges? Agreed? Now, that means its sum is that. And 1 plus 1/3 is 4/3, and that gets you 6/4, and that gets you 3/2. So hopefully you dealt with the fractions correctly. Now, not all series are written out in this format, right? Each individual term. It's just as common that you might get it might be written in its sigma notation. That dot there is just a, I don't know what happened. I'll write it again so it's not there. Might look like that. Now that is a geometric series as well. It's just written down in sigma notation. The problem with sigma notation, until you get comfortable with it, is don't we need to know those two guys? That's all I really need to know. What is the first number, A, and what is the value of the common ratio? Great. So if you want to know what the first number is, don't you just plug n equals 1 into this? And so what does that get me? It gets me 4 times 1/3. Well, actually 4 times 1/3 to the power of 0. Be careful here. What is 1/3 to the power of 0? What number is it?
1.
1. So it's 4 times 1, so it's 4. Great. Now, what is the common ratio? Well, I guess I could find the second term and divide, but it's actually quite easy. See that guy there? That's your common ratio. Right, is this guy going to converge or not?
It will.
It'll
It will.
converge.
And can't you do the S equals A over 1 minus R and all that stuff? So I'll say dot, 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 right? So basically, if you see it in sigma notation, shouldn't you just plug the first N or K, whatever letter of the alphabet they're going to use on you to get A? And won't this guy over here be the one? Let's try another one of these guys. How about sigma n equals 1 to infinity of 5 times 2/3 to the power of n? Let's do the easy one first. What's the common ratio on this geometric series?
2/3.
2/3.
Right. Now, A is not 5. A is the first term. Isn't A what you get when n goes 1 in this case? So that's going to be 5 times 2/3 to the 1, which is what, 10/3. Right, it still converges, right? And you should be able to find out what it converges to in the usual way. Right. Will you all say hi? Because we kind of